Understanding the scenario, we are examining the relationship between the prices of two inputs, x1 and x2, in a production process. We'll utilize a Cobb-Douglas production function, a widely used model in economics that represents the relationship between inputs and output. Assumptions. Production function, U equals AX. 1 caret alpha asterisk, x 2 caret beta. U represents the level of output. X1 and x2 are the quantities of the two inputs. A, alpha and beta are constants. A is a technology parameter. Alpha and beta represent the output elasticities of inputs, x1 and x2, respectively. They indicate the percentage change in output resulting from a 1% change in the respective input. Budget constraint Px1, x1 plus Px2. x2 equals M. Px1 and Px2 are the prices of inputs x1 and x2, respectively. M represents the total cost budget available for input purchases. Objective. Determine whether the price of one input, e.g., Px1, directly influences the price of the other input, Px2. Methodology. We'll employ the method of Lagrange multipliers to find the optimal input combination that maximizes output subject to the budget constraint. Step-by-step derivation. 1. Formulate the Lagrangian. The Lagrangian function combines the objective function, production function, and the constraint. L of x1, x2, lambda equals ax1 caret alpha x2 caret beta plus lambda mpx1 x1 px2 asterisk x2, where lambda is the Lagrange multiplier. 2. Determine first-order conditions, FOCs. To find the optimal input levels, x1, x2, we take the partial derivatives of the Lagrangian with respect to x1, x2 and lambda and set them equal to 0.
L, x1 ίσον alpha a ή x1 circumflex, alpha 1. x2 circumflex β αλλού 1 ίσον 0. L, x2 ίσον β a ή x1 circumflex alpha x2 circumflex β 1, λου 2 ίσον 0.
Partial differential L/partial differential lambda equals mpx1x 1 minus px2 x2 equals 0. 3. Derive input demand functions. From the first two FOCs, we can isolate the terms involving lambda.
Alpha a x1 circumflex, alpha 1. x2 circumflex β, lambda ίσον px1. Β a x1 circumflex alpha x2 circumflex, β 1, lambda ίσον px2.
Dividing the first equation by the second equation, we eliminate lambda. Alpha/beta asterisk x2 by x1 equals px1 by px2. Rearranging, we obtain the optimal input ratio. x2 by x1 equals beta/alpha asterisk px1/px2. This equation reveals that the optimal ratio of inputs, x2 by x1, depends on the ratio of their prices, px1, px2, the output elasticities of the inputs, beta/alpha. 4. Interpreting price independence. The equation x2 by x1 equals beta/alpha asterisk px1 px2 demonstrates that the optimal input ratio is determined by the relative prices of the inputs and their respective contributions to output. Crucially, this equation does not imply a direct causal relationship between the prices of the two inputs. The prices, px1 and px2, are determined by market forces of supply and demand for each input. The firm's decision-making process, as reflected in the optimal input ratio, responds to the existing prices. Conclusion. In the context of this Cobb-Douglas production function and the given budget constraint, the price of one input, e.g., px1, does not directly determine or influence the price of the other input, px2. The prices are established by market factors, independent of each other. The firm's optimal input choices are a function of these independent prices and the production technology, represented by the parameters alpha and beta.